In this lesson, we're going to teach you how to make millions of dollars off the distributive property. I'm being a little facetious, but not really. So let's look at the distributive property. It goes hand in hand with the associative and commutative properties, which we just learned about. It's one skill that students get wrong quite often on the exam, so it pays to learn this very well. Distributive property says A times quantity, B plus C in parentheses, equals AB plus AC. And effectively that occurs by A, the term, can be multiplied by B independently, and that forms A times B plus A multiplied by the C separately, and A times plus C is plus AC. So when we go in this direction, we would effectively say we are expanding the expression. That can be quite useful for being able to manipulate expressions and solve equations. And likewise, going in this direction, we would generally call factoring the expression, which is to say I see a hidden factor in the products of each term, a hidden A. In this case, it's not really hidden, it's quite visible, and I can pull that A out of the expression. And factoring can be quite useful too for manipulating expressions and ultimately solving equations. So in either direction, factoring or expanding expressions, you want to get pretty good at the technique. The distributive property can come in very handy doing some quick, accurate mental math. Let's suppose we have 107 times 60. I can break that out to a statement much like A times B plus C. Essentially, I know 107 is 100 plus 7, which will be individually easier numbers to multiply with 60. And according to my distributive property, that's really just 100 times 60 plus 7 times 60. So I can do those calculations in my head, probably don't even have to write it down on paper. 60 times 100 is 6,000, and 60 times 7 is 420, and I can add those up, 6,420. A much easier way in many cases than doing your full math of 60 times 107 and multiplying it out, 0 times 7, well those would be 0 and 0, and 6 times 7 is 42, carry the 4, 6 times 0 is 0 plus 4, 6 times 1 is 6, and I'll get there, but it's not as obvious, and I certainly need to write it on a piece of paper. Whereas the distributive property, just that exercise of breaking things up into components and manipulating those components that are more easily calculated will be very effective and go a long way on the exam. The distributive property will also be essential in algebra. For example, 5 times quantity x plus 2 would distribute out to, again, 5 times x is 5x plus 5 times positive 2 is plus 10. We could even expand the complexity of this situation into the multiplication of two different binomials, where the word binomial, as we'll see in later lessons, is just a fancy way of saying there are two terms added or subtracted together. And they will result in a polynomial, which is another fancy way of saying there's just more than two terms added or subtracted. And in this case, we've got the x minus 1 together. So really that's x times our x plus 2 minus 1 times our x plus 2. And we have two instances of our first example up above, in which case I do x times x, which is x squared, and then x times plus 2, which is plus 2x, and minus 1 times x is minus x. We don't need to write the 1 coefficient. And minus 1 times 2 is minus 2. And that works out to, if we consolidate the 2x minus x, which just becomes plus 1x, that's x squared plus x minus 2. And that method is often referred to as the FOIL method. But be careful, you want to avoid some typical mistakes students make in distribution. 10 minus 2, x minus 5, for example. That does not equal 10 minus 2x minus 10. Not true. In this case, remember that negative sign out front needs to be multiplied through and distributed to each term within the parentheses. So let's break that out. 10 minus 2 times x is minus 2x, but then the minus 2 times the minus 5 turns that to positive 10. The double negatives make a positive. And that's where students typically make their mistake. They forget to associate the two negatives, which multiply out while expanding the expression to become a positive. Okay, so that's one typical mistake. So always beware if you have a negative sign in front of a parentheses and there's a negative term within the parentheses. The other one is a plus b squared. It does not equal a squared plus b squared. That is not the case. I can't just simply take my exponents and apply them to each of the individual terms. Why? An exponent means the entire expression is multiplied together that many times. So a plus b squared is literally a plus b times a plus b. And now we're doing that binomial or polynomial expansion we saw a second ago. It will be a times the first term in the second, that's a squared, plus a times plus b, the second term, the first term with the second term in the second parentheses, and that's plus ab. And then we'll have to take the second term in the first parentheses, multiply that through each term of the second parentheses. And that's plus b times a, so that's plus ba, and plus b times plus b becomes plus b squared. And we know BA and AB, thanks to our commutative property of multiplication, are essentially the same thing. So that becomes a squared plus 2ab plus b squared. Very different than just a squared plus b squared. Another typical mistake students make also has to do with exponents. It's the difference between 3n squared, which is not equal to 3n in parentheses squared. Not true. Why? Because 3n in parentheses, here we've got the product of two terms, not the summation or difference of two terms as we saw in example 2, but the product. We do want to apply the exponent to each individual term. We have to square the 3 and we have to square the n. And the result is 3 squared times n squared, which equals 9n squared. So you can't forget to square that coefficient of the variable as well. And if we want to see that, literally 3n squared is 3n multiplied by 3n. And I can reassociate, thanks to the associative property of multiplication, that to 3 times n, and that is essentially our 3 squared times n squared, just to prove that we get that result. So let's have some fun with some examples of the distributive property. What if I had 9 plus 99 plus 999 all divided by 9? What could I do with that? Well, one thing I know is that every term in the numerator has a hidden factor, that is, number multiplied by other numbers to make that result. So what that would really be is I could draw out that 9 or distribute it out. 9 times 1 plus 9 times 11 makes 99, plus 9 times 111 makes 999. So I found that hidden 9 and I drew it out from the expression, at which point I know I'm dividing by 9. I can simply cancel terms in this case. And my result is 1 plus 11 plus 111, which is 123. Without a calculator, the distributive property has helped me see a hidden 9 in the product of every term and evaluate the expression. What about something like the following? And we may not have seen factorials yet, we will soon, but essentially that means 6 times 5 times 4 times 3 times 2 times 1 for 6 factorial, and 5 factorial would just be 5 times 4 times 3 times 2 times 1. But what the heck do I do with it when I'm adding factorials? Again, I might be able to distribute something out, some factor I will see hidden among the 6 factorial, the 5 factorial, and I really note that 6 factorial is just 6 times 5 times 4 times 3 times 2 times 1, which we just said is 5 factorial. So it's 6 times 5 factorial plus 5 factorial. And now I know I have that hidden 5 factorial, no longer hidden, I've made it fairly explicit. Within this expression, I can distribute out my 5 factorial, and I will have 6 plus 1. There is 1 times 5 factorial, even though we don't show the 1 as a coefficient. And that in turn is just 7 times 5 factorial. So again, I've used the ability to find a common factor somewhere in there to pull it out from the expression thanks to my distributive property. Let's see one more example. Okay, x squared minus y squared over x minus y. Well, can I just say that x minus y cancels out and the result is x minus y? No, I can't do that. For the same reason that a plus b squared is not the same thing as a squared plus b squared, fairly analogous to that. But I can find a hidden factor in there of x minus y that I might be able to use. And in fact, I note that this is a difference of two squares, and the factors of a difference of two squares is x plus y times x minus y. And as I multiply that out, that's x times x, which is x squared, x times minus y, which is minus xy, and then the second term, y times x, is plus xy, and y times negative y becomes minus y squared. In this case, my minus and plus xy zero out, and I'm just left with x squared minus y squared. So in fact, my factoring is correct of x squared minus y squared, which I can then divide by my x minus y. So let's rewrite that out on the left side here. X plus y times x minus y over x minus y. And again, given the horizontal fraction bar, it's assuming grouping, but I know the value with this expression must be the same as the value of this expression because they're exactly the same, and they're not added and subtracted in the numerator, they're just a product of x plus y and x minus y. So I can essentially cancel those, that becomes 1, and my answer is just x plus y. And I was able to do that, again, by distributing out binomial factors in this case. I found another common hidden value. And in finance parlance, when you can evaluate different components within larger expressions and put them together and pull them apart to make new expressions or evaluate the whole, that's called something we refer to as arbitrage, or something very much like it. And people who can do arbitrage very well in New York City and elsewhere make millions of dollars. So at first, at the outset of this lesson, I was kind of being facetious, but then again, not really. In fact, there are more math geeks rolling around in Mercedes and Bentleys than there are movie stars and professional athletes combined, by far.